We previously discussed intramolecular forces, which are the electrostatic attractive forces within specific molecules. Now what we're going to talk about are intermolecular forces. Even though they sound similar, they're very different. Intermolecular forces are actually the attractive forces between different molecules. Before we get into the details of the four different types of intermolecular forces that you need to know about, though, there's an important question that you need to answer. And that question is, why are intermolecular forces weaker than intramolecular forces? So what I want you to do right now is pause this video and, keeping in mind Coulomb's law, provide an explanation using his law for why intermolecular forces would be weaker than intramolecular forces. Alright, so there are actually two reasons for why intermolecular forces are weaker than intramolecular forces. The first one, the one that you should have gotten, is the fact that intermolecular forces are between molecules, and as a result, the distance between these electrostatic charges between the two molecules is much greater than it is within a specific molecule, and therefore the attractive force based on Coulomb's law is much weaker. The other explanation, which we'll look at, is the actual charge when we're dealing with molecules is much smaller than when we're dealing with ions or with electrons in covalent bonding. And so as a result, intermolecular forces are much weaker. Number one, because the distance between the entities involved is much greater, and also because the charge involved is much smaller. So we need to keep that in mind. Intermolecular forces are extremely important, but they will always be much weaker than intramolecular forces, which include ionic bonding and covalent bonding. So let's talk about the first type of intermolecular force, and this is dispersion forces. Now, all substances, no matter whether they are polar or nonpolar, they will all have dispersion forces. And so what I need to do, this is one of the harder intermolecular forces to really understand how it is created. And so I'm going to go through and explain it. So if you look at this diagram right here, you have A, and you're looking at two helium atoms in A, and they're not polarized, meaning those atoms are not polar. And the reason why is, on average, the distribution of the two electrons in helium are not situated either completely on the right, completely on the left, or completely at the top or the bottom of the atom. Instead, on average, they're evenly distributed. However, as you can see in B, in that middle section, at one instance, in 1 second, those electrons can line up. Then they'll go back to being evenly distributed again, but they can line up on a specific side. So in B, as you can see in atom B, those electrons have lined up on the left-hand side. So, based on what we learned previously, if those electrons have lined up on the left-hand side, that means the left-hand side of the atom is now partially negatively charged, which means the right-hand side, which has lost those electrons, is now partially positively charged. Okay, so now we suddenly have a polar atom, and that's instantaneous because it will go back to being not polarized just as easily as it became polarized. Now, if you look at C, what happens once atom B has a dipole, it will induce a dipole in A, meaning it will create a dipole in atom A. So as you notice, since atom B has a partial negative charge on the left-hand side, that will cause the electrons in atom A to be pushed over to the left-hand side because electrons repel electrons, causing the right-hand side of atom A to have a partial positive charge and the left-hand side of atom A to have a partial negative charge. Now, if you notice for C, the bottom part, it shows the partial positive and the partial negative. That attraction between the partial positive and partial negative, that electrostatic attraction, that is a dispersion force. So as you can see, molecules don't have to be polar or nonpolar. They can be one or the other to have dispersion forces, and therefore all substances have dispersion forces. Let's talk about now what affects the strength of these dispersion forces. Right, there are two different factors that can affect the strength of dispersion forces. The first one is the polarizability of a molecule. Now, the polarizability is the ease with which the charge distribution can be altered. So as you saw in helium, we were able to shift the electrons to the left-hand side and create that dipole. Well, if you have more electrons, that ability to instantaneously push those electrons to one side to create a dipole, the more electrons you have, the easier it is to do, and therefore the stronger the dispersion force will be. Therefore, as the number of electrons in a molecule increases, the strength of the dispersion force also increases. And as a result, larger molecules, since they have more electrons, they have stronger dispersion forces. So that's the first one. The larger the molecule, the stronger the dispersion force because of the increased polarizability, the ability to polarize a molecule. So as you can see from this table right here, what this graph is showing is that as your molecular mass increases, the dispersion force also increases. So it doesn't show this directly, but let's compare neon and fluorine. Now, fluorine has a larger molecular mass, and notice its boiling point is higher. Now, if you think about it, the boiling point is the point at which a liquid goes from a liquid to a gas. So if the attraction between the molecules is larger, that means that the temperature at which a liquid can go from a liquid to a gas, it's going to be a higher temperature. It's going to require more heat. Therefore, even though it doesn't specifically say dispersion forces in this graph, boiling point is equivalent to that, because as the boiling point increases, that means that the attractive forces between molecules is increasing. So if you look at the bottom one, xenon and iodine, iodine has much stronger dispersion forces, and you can see that because it must reach 458 Kelvin in order to go from a liquid to a gas, while xenon only needs to reach 166 Kelvin. Now, the other factor that affects the strength of dispersion forces is molecular shape. Molecular shape affects it because as you increase the amount of contact that can exist between molecules, that increases the dispersion forces. So what you should see here in this diagram, the top one is a linear molecule. So if you can imagine the N-pentane, that has a greater surface area in which the molecules can interact with each other and therefore create those induced dipoles and therefore have that dispersion attraction. Now, if you have a spherical model, as you can see below, there's less surface area, there's less area in which the induced dipoles for the two different molecules can interact, and therefore the attractive force between the molecules is less. The second type of intermolecular force that I'm going to talk about is dipole-dipole forces. Now, why do I say dipole-dipole twice? Well, because you have two molecules, and each of them has a permanent dipole. Okay, so we're not inducing dipoles anymore. They permanently have that dipole. They have that partial positive and partial negative charge, and the dipole-dipole intermolecular force results from the electrostatic attraction between those partial dipoles. So as you can see in this diagram on the left-hand side, the blue part represents a partial negative charge, while the white atom represents a partial positive charge. And so you can see in red those attractions between the partial positive and the partial negative. This is extremely similar to dispersion forces, except for the fact that dipole-dipole forces are permanent. They always exist like that, and therefore dipole-dipole forces are stronger than dispersion forces because that dipole is permanently there. What B actually shows you, interestingly, A is a solid, and so you have that clear structure in which the partial positive and partial negative sides of the molecules are attracted to each other. When you have a liquid, however, you might actually end up with a partial negative next to another partial negative. And so what that shows, those blue dotted lines represent repulsive forces. And so when you have a liquid, the attractive forces are much weaker because molecules might line up in such a fashion that they actually repel each other instead of constantly being attracted to one another. So what this diagram shows you is that assuming that the molecules have similar molecular weights, the strength of the intermolecular forces increases as the polarity of the molecules increases. All right, if we look at this graph right here, what this is showing you, if we ignore water, HF, and NH3, what this shows us is that when you have non-polar molecules, okay, the strength of the intermolecular forces increases with increasing molecular weight. And this is what we expected based on what we had discussed regarding dispersion forces. Keep in mind, dispersion forces exist for both polar and nonpolar molecules, while dipole-dipole forces exist only for polar molecules, molecules that have a dipole. Now, let's talk about water, HF, and NH3 really quickly because those do not conform to the pattern that we expected. So there's clearly another intermolecular force that is involved. And that intermolecular force that's involved is hydrogen bonding. Now, hydrogen bonding is actually a type of dipole-dipole attraction, which tells us that in order to have hydrogen bonding, the molecule involved must be polar. That's the first thing. And hydrogen bonding occurs between hydrogen of one polar molecule and the F, O, or N atom in another molecule. And so we'll see what that looks like in just one sec. Here on the right-hand side, you've got water, you've got HF, you've got NH3. And as you can notice, this intermolecular force is the attraction between two different molecules. So for the top one, for water, that hydrogen is attracted to the lone pairs of electrons on oxygen. That attraction is called hydrogen bonding. Now, hydrogen bonding is stronger than dispersion forces and it's stronger than dipole-dipole forces. And the reason why is that hydrogen has such a low electronegativity, while fluorine, oxygen, and nitrogen have such a high electronegativity that the large partial positive and partial negative charges that are involved result in a stronger attraction than what we would typically see in dipole-dipole attractions. Alright, there are a number of different biological implications of hydrogen bonding. In proteins, as proteins go from being just polypeptide chains to actual proteins with 3D structures, those 3D structures are being able to be created because of hydrogen bonding. For DNA, when we're talking about a double helix, the attractive force, that bond that allows the two strands of DNA to attach to one another, is hydrogen bonding. Now, the important thing to remember is that hydrogen bonding, while it's strong, it is not as strong as covalent bonding. And so as a result, that allows DNA to break, the two strands to break apart when we need to replicate the DNA, either in DNA replication or when we're creating RNA. The other important thing to think about when we're talking about hydrogen bonding is something that you observe every day. Now, solids are normally more dense than liquids, but when we're looking at water, water is actually more dense than ice. In forming ice, the water molecules, because they are forming strong hydrogen bonds, they conform themselves in such a fashion, as you can see on the bottom, that there is a larger distance between the water molecules than you would typically see with water when it's in its liquid form. And therefore, because of that large distance between the water molecules and ice, ice is less dense than water. The last type of intermolecular force that we need to talk about is ion-dipole forces. Now, you experience ion-dipole forces every day. This occurs when you take a polar molecule and you dissolve an ionic compound into it. So as you can see in this example looks kind of complex, but it's actually just salt dissolved in water. So as you can see, the ions from that ionic compound break apart, and then the chlorine ion, which is negatively charged, it's attracted to the part of the water molecule that's partially positively charged. And so as a result, the chlorine ion is going to be surrounded by water molecules with their hydrogens facing towards chlorine. This solvation of chlorine results because of the negatively charged ion and the partial positive charge in this polar molecule. Now, in reverse, the sodium ion is going to be surrounded by the water molecules, but what's going to be facing the sodium ion, which is positively charged, is the partial negatively charged part of the water molecule, the oxygen. Alright, so there are two rules in general when we're considering all the different types of intermolecular forces that you have to keep in mind, and I actually took this straight from your textbook because I couldn't have said it any better. The first one is that when the molecules of two substances have comparable molecular weights and shapes, dispersion forces are approximately equal in the two substances. Okay? Any difference in the magnitude results from dipole-dipole attractions. So if you have two molecules that have similar weight and shape, if they have different intermolecular forces, if the strength of their intermolecular forces is different, that is a result of dipole-dipole attraction. Now, those dipole-dipole attractions, their strength increases as the polarity of the molecule increases. And if molecules are capable of having hydrogen bonding, that's going to be the strongest attraction. The second rule is that when the molecules of two substances differ widely in their molecular weights, dispersion forces are what actually dictate the strength of the intermolecular force. So the larger the molecule, the stronger the intermolecular force.